Good day everyone, I am Z-MB Mendoza and today I will be presenting my study entitled Enhanced Tetracycline Removal via Innovative PVDF δ-MnO2 Photocatalytic Membrane Reactor in partial fulfillment for my degree of Bachelor and Master of Science in Biological Engineering. So I will give you a brief overview about my study followed by the objective, methodology, data, and then a conclusion. Tetracycline is an emerging contaminant that is very much of a concern because not only it induces toxicity to aquatic systems, but also it induces antibiotic resistance, which is a pressing global threat. Sources include humans, animals, hospitals, households, and pharmaceutical effluents. So this can greatly affect the environment negatively, like for example, due to this it can cause disruption of the microbial communities, and most of all, it will impact our health or human health, no? Since these AR, the antibiotic resistant genes and antibiotic resistant bacteria can be acquired by humans, thereby reducing the efficiency of tetracycline. So current treatment plans include biological, chemical, and membrane-based. For biological, they are cost-effective and environmental friendly, but may facilitate the spread of antibiotic-resistant genes. For chemicals, they are effective but are very costly. For membrane, they only induce separation and are very much prone to biofouling. So what we aim here is to employ membrane-based technology with chemical method, particularly advanced oxidative process, to filter and degrade tetracycline. So to do that, we aim to fabricate the membrane, the PVDF membrane, and coat it with δ-MnO2. Our methodology comprises three major parts: the catalyst synthesis, which is divided into three stages: the Mn-100 synthesis, the carbon encapsulated MnO synthesis, and the formation of the final form of the photocatalyst, which is δ-MnO2. And then the second part is the membrane fabrication, which consists of creating casting solution. And then the last part is the spray coating part, which consists of creating coating solution and the spray coating itself. Now, finally done with the methodology, let's now move on to results and discussion, which will be divided into two parts: the MnO2 characterization and the membrane characterization. No, so we divide it into two in a way that we can confirm the synthesis of the δ-MnO2, and the second part, which is the membrane, to confirm the successful coating of the MnO2 against the membrane, as well as the evaluation of its performance. So the first one is the XRD plot. We can see here 12.4 degrees, 25, 37.2, and 66.2, which corresponds to these four planes. No? So it matches with JCPDS card 80-1098, which corresponds to XRD plot for δ-MnO2, and thereby signifying the successful formation of δ-MnO2. Now for the FTIR, we can see here significant peaks at 586, which corresponds to MNO bonding, and then at 3,340, which corresponds to OH vibration. Now, so these peaks are very much similar to that of the peaks obtained from previous studies. And then this broad peak at 1,521 and 1,268, we deduced that it was from the residual carboxylate group from the trimesic acid that we used in the formation of our MOF, the first stage of catalyst synthesis. And then for the end-to-end desorption, we can see here that we have here type 4 isothermal H hysteresis, which just means that majority of our pores are mesoporous, which means that our pores span about 2 to 50 nanometers in diameter. Then we also have here and we can also see here that some of the pores are microporous, which means that diameter is about or less than 2 nanometers. And then another important thing to take note of here is the decrease in surface area as we go through the stages of photocatalyst synthesis. So This just highlights the importance of starting with MOF first because it has a very huge surface area, so that eventually we will have a decent um, surface area as we reach the final form of our photocatalyst, which is δ-MnO2. Now for the SEM, we can see here that we have here spherolytic structures of about 400 nanometers in diameters and a formation of flower-like structure. And for the DEM, we can see that δ-MnO2 has indeed layers which are consistent with the findings in the previous studies. Now, observing the optical properties on the left side, we can see here that it has um, it has a peak of about 560 nanometers, and on the left side we can see here a band gap of 1.56 electron volts, both consistent with the findings in the previous studies. Now for the XPS, we can just see here that we have here the peak for manganese, oxygen, and carbon from, again, the residual organic compound from the trimesic acid, which just confirms the successful synthesis of photocatalyst. Now, finally, we move on the last part of our results and discussion, the membrane characterization. So the SEM of the membrane, we have here the MO, M1, M3, and M5. MO serves as the virgin, or the one without the coating. So we can see here the top layer of MO, it is very much smooth, and then at the cross section and near the top we can see here the presence of macrovoids, and then the center we can see here a very porous structure, and at the bottom again is a smooth surface. So as we compare it with other membranes, M1, M3, M5, which are the membranes that are coated, we can see at the top surface that there is a formation of this flower-like structure, which we have observed earlier in the SEM of the δ-MnO2 alone. And then at the cross-section and near the top, we can see here that there is still a macrovoid structure, which means that δ-MnO2 did not disrupt the macrovoid structure and as well as did not penetrate the membrane. And then for the center, it's the same, and then for the bottom surface, it is still the same, meaning the δ-MnO2 did not affect the bottom surface of the membrane. For the coating thickness, we can see here that as the concentration increases, the thickness increases as well. Now observing the pores characterization, we have here as we observe both the porosity and the pore size, there's a general trend wherein as the concentration increases, the porosity and pore size decreases. And then at figure C, we can see here the dynamic water contact angle. We can see that initially the membrane is hydrophobic, but eventually as we increase the concentration, it becomes hydrophilic. For the FTIR at figure A, we can see here that the black plot, we can see that it still has the characteristic peaks of the PVDF, but eventually as the concentration increases, um, the characteristic peaks of this PVDF is being masked. And then the peaks for the MnO2, as we observed earlier on the characterization of δ-MnO2, uh, appeared and tends to increase as we increase the concentration. Now at XPS, we can see here that the MO still has a peak for fluorine, and then eventually as the coating increases, it decreases, and then MnO2, Mn and oxygen peaks increases. Now for the kinetics, we can see here that the figure A is the pure water flux, and then the letter B is the tetracycline flux. For letter A, for figure A, we can see that generally it has MO has a high pure water flux, and then eventually as the concentration of the coating increases, the um, the flux decreases, and same goes with the tetracycline, but in here we can see that the trend in here is much lower than that of the pure water flux, and um, this can be deduced from the presence of tetracycline molecules, which can hamper the existing pores and thereby reduce the permeability of the membrane. But there is a trade-off between flux and separation efficiency. No, so although we have a reduced flux in here, we have a very high separation efficiency. We can see here that at MO, it might have the highest flux among the four because of the lack of coating, but it has the lowest separation efficiency. And then as the coating concentration increases, the separation increases. The separation efficiency increases. We can see here that M5 has the highest of about 96.1%. And then we have here the LC mass for the redentate, so we can observe the presence of TC on the redentate. On a zoomed in version, we can see here that at MO, there is still a very prominent peak for TC, the one in the red at 445 daltons. No, so we can see that as we add the coating at 1% and 3%, the peak generally um, decreases, which means that there is a partial degradation of TC at the redentate. But as we observe the M5, there is no peak at all. There is no detectable peaks at all, signifying complete degradation of TC at the redentate. Now moving on with the LC mass of the permeate, because of course we have to observe the presence of TC on the permeate. No, this is like the clean water sort of. So we can see here on a zoom-in version, the permeate, there's a decreased um, peak for TC, the red one, because huge chunk of it have already been separated by the membrane. And then as we move further, we have here M1 and M3, um, still a reduced peak for TC, but still there. And finally, at M5, again, we achieve complete degradation, meaning we don't have the presence of TC at the redentate and then the permeate. Now, after learning about the kinetics and the degradation of the tetracycline, we now have to determine the participating radicals on the degradation, no? And this can be determined through scavenger test, no? So sodium azide corresponds to singlet oxygen, and then third butanol for hydroxyl radicals, and TOA for holes, no? So as we added these three chemicals, we can see that there is no difference with the degradation of TC, meaning um, all of the radicals that correspond to these chemicals are involved in the degradation of the tetracycline. So our proposed mechanism, our reaction mechanism for its degradation is that as UV, or as the visible light, hits the photocatalyst δ-MnO2, this created an electron hole pairs. So these holes may react with water and then produce hydroxyl radicals, which can readily degrade tetracycline. And then these electrons can also react with oxygen and in turn create superoxide radicals. So these three superoxide radicals, hydrogen ions, and hydroxyl radicals can further react with one another and create singlet oxygen and water. So this singlet oxygen can readily degrade tetracycline. Now finally onto the stability, we can see here that once we check the absorbance and plug it in this calibration curve, we'll be able to get the MnO2 concentration. And now with the M5 after immersion, we got MnO2 concentration of 18 micrograms per liter, which means that the coating is very much stable, and this concentration might just be from the loosely adhered MnO2 and not the actual degradation of the coating. In conclusion, we can see that this hybrid system is very much efficient and effective because we can see that we obtain 96.1 separation efficiency and complete TC degradation, meaning we have a complete TC removal with the PMR system. Not only that, it is also stable, making it economically sustainable. So for future study, we advise to investigate the antifouling capabilities as well as the antibacterial and the potential toxicity of the degradation intermediates. That's all. Thank you. Have a good day, everyone.